All right, now it's finally time to do the hard part. We're gonna write our own algorithm that will find the lowest cost. And this is the famous gradient descent algorithm. And gradient is, well, you guessed it, just another word for slope. So I'm going to give you a very, very Austrian perspective to think about the gradient descent algorithm. You know, we've got a lot of mountains back in Austria, and they're very, very beautiful, and you can go ski down them. But a mountain is a force of nature. You have to respect the mountains. You see, the weather can change very, very quickly. And this is especially unpredictable in winter and at high altitude. So, imagine yourself that you've wandered off the beaten track and the fog comes rolling in. And at this point, you find yourself in a survival situation. This is when you can't see very far and you can only feel the ground beneath your feet. The cold is going to be creeping in through your jacket, and you find yourself thinking, how do I get down? How do I get back down? Well, to figure out which way is down and towards that hot cup of tea waiting for you at the end of your journey, you gotta feel like which way is down. What is the slope, right? You're gonna look at your feet and you're gonna figure out that the fastest way down is in the direction where the slope is steepest, right? Where the descent is the most steep. And if you take a step downwards in that direction and then kind of get a feel for it again, like which way is the slope, and then take another step where the slope is steepest, you'll be down in that valley in no time and you can sip on that hot cup of tea, right? And this is how you can think about gradient descent. Except instead of a mountain, gradient descent is going to take place on a cost function. And the cost function actually doesn't tend to look like this. It doesn't kind of have a peak, if you will, right? Because if a function had a peak, then it would be called concave. It has a maximum. But with our cost functions, we're going to be looking for minimums, right? So if you imagine that mountain flipped upside down, and all you've got is a valley, right, that you have to kind of find, then your cost function is going to look more like this. This is a kind of function that's called convex. It'll have a minimum, and our job is to get to the bottom of it, because that's where the cost is lowest. Now, gradient descent isn't always called gradient descent. There's another word for it that you might see as well in the literature. Sometimes it's referred to as steepest descent. And yeah, it's an optimization algorithm for finding the minimum of a function. So, to think about our mountain example, to find the minimum, the function takes these little steps, right? It takes a step in the direction where the slope is steepest, in the direction of the negative of the gradient. And bit by bit, ends up in the bottom of the valley. All right, so let's implement this in Jupyter Notebook. Let's add another markdown cell here. And I'm going to go to cell type markdown, and put 2 hashtags there for a section heading. And that section heading is going to be Python loops and gradient descent. Now, if you're a seasoned programmer, you're going to be familiar with writing loops. But if you're new to Python or you're new to programming, then the next couple of minutes are going to be the introduction to this topic of loops. Loops are little bits of code that are executed over and over again. We're going to walk down that mountain. We're going to walk down into the valley with our gradient descent algorithm. So this is going to be a very, very useful tool for accomplishing that, because our algorithm has to complete that famous 3-step process, right? Predict, calculate error, and learn. And repeat. So instead of writing the same Python instructions over and over again, we're going to be using loops to simplify that for us. Speaking of for, this is the first loop I'm going to introduce to you guys. So this is going to be the for loop in Python. So I'll I'll just write a little comment here. Python for loop. And this is what the syntax looks like. We're going to have the keyword for, and then there's going to be a variable. In this case, I'm going to call it n. And then another keyword, in, and then I'm going to say range, parentheses, 5, colon, new line, and now we're inside the loop. And here we're going to print famous first words, hello world. Okay, let's hit Shift Enter and see what happens. All right, so we've printed hello world 5 times, right? 1, 2, 3, 4, 5. If I change this range to 3, it'll print it 3 times. If I change it to 1,000, it'll print it 1,000 times. But let's stick to 5 for the time being. And let's take a closer look at this value n here, right? N is just a variable, and it's going to keep track of how often our for loop has run. So if I say hello world, comma n, then I can see what the value is of the variable n each time the loop is run. So it starts at 0. Programmers like to start counting from 0. And that's the very first time the loop runs. Then this print statement is executed another time. So second time, third time, fourth time, fifth time. And at this point, the loop stops, right? Show you that. Print end of loop. So the Python program will come in here, it'll execute whatever is inside the loop, and you can tell what's inside by the spacing, a predefined number of times. In this case, 5 times, right? 0, 1, 2, 3, 4. Now we can call a little counter variable here, n. We can call it I. This is another one that is often used. So if I call it I get exactly the same result. It really doesn't matter what you call it. You can call it counter. As long as you're consistent, you can access the variable, the looping counter, inside of the loop by its name. All right, so that's the for loop. It executes a predefined number of times, and it's got this very, very simple syntax. For n, in, range, and then some number here. So this is how oftentimes you want to execute the loop. With that out of the way, let me show you another type of loop. This type of loop is also very, very common, and this is the so-called while loop. Yeah. A while loop works a little differently, right? It has a condition that it checks every time it runs, right? So it'll check the condition, and then if that condition holds, it's going to run the code inside the loop. And it's going to continue doing that until the condition fails. So if I have a counter and I say it's equal to 0, and then I can write my while loop like this. I can say while, which is a keyword, and say counter is smaller than, I don't know what, 7, colon, print counting counter. So I'll print the value of my counter inside my loop. And then I'll say counter is equal to counter plus 1. So I'm going to increment my counter variable by 1 every time the loop runs. And then when I finished with the loop, I'll print something else. Yeah. Ready or not, here I come. Yeah. Let's make that loop a little bit more menacing than the last one. So if I hit Shift Enter now, I can see my print statement inside my loop executed 7 times, right? Starts at 0 and executes it until our condition fails. This is the condition. So whatever follows the while keyword is the condition that's checked. And this fails when counter is equal to 7, because 7 is equal to 7. It's not smaller than 7. So this will be false. At this point, the loop terminates, and the code inside is not executed anymore, and we jump to our print statement below, right? This one, ready or not, here I come. And this is what we're seeing here. Again, I can accomplish the very, very same thing as with the for loop. So I can execute it 5 times. So if you want, you can also execute a while loop a predefined number of times. But yeah, there's a small catch. There's a small gotcha that can happen with while loops that you won't get with for loops. Any guess what this gotcha is? Any guess what it is that can trip you up and where you can shoot yourself in the foot? So with while loops, you can get into a situation where they don't stop, where they don't terminate. So for example, if I had made a typo here, and instead of that plus, I had hit minus, then my loop would actually run forever, right? Because it would start at a 0, then when it reaches this line, my counter would go to -1, then would come here and go to -2, and then would come here, -3, and this thing would just continue going, right? Which is clearly not my intention, right? It would continue going and cause a lot of problems. So with while loops, you have to be careful that you don't accidentally write an infinite loop. Yeah. So for loops, by their very nature, run a predefined number of times. While loops run while a certain condition holds true. And this is where you gotta be careful. So with your while loops, you gotta make sure they terminate. And the easiest way to remember this is with an old programming joke. Yeah, that goes something like this. A programmer once said to his wife, "Honey, I'm heading to the supermarket to buy some groceries." To which his wife responded, "While you're there, buy some milk." And alas, he never returned home again. Oh, crickets. Back to gradient descent. Let's tackle that in the new cell here at the bottom. The thing with gradient descent is that we need a couple of ingredients, right? We need a starting point, then we need a learning rate, and we're going to need some maybe temporary value to hold on to something while our program is executing. So I'm going to create these 3 things here. I'm going to say new x, which is going to be our starting point. I'm going to set it equal to 3. We're going to start with 3 as the starting point. I'm going to say previous x, and this is going to be my temp value, if you will, that only matters inside of the loop. And then I'm going to also specify a learning rate, yeah, or gamma, or whatever you call it. So I'll call it a step multiplier. And I'll set it equal to 0.1. Now it's time to write that loop. So it's going to be a for loop for us. So I'm going to say for n in range, and maybe start at 30, colon. And now for the first step. What's the first thing that we have to do? Well, we have to make a guess, right? We have to make some prediction. This is step 1 of the machine learning process. So I'm going to take our temp value, previous underscore x, and I'm going to set it equal to our random guess. Yeah, new x equals 3. 3 was a random guess, just our starting point for our gradient descent. So I'm going to set them equal to each other. And now we get to step 2. Step 2 is calculating the error, because we need to know how far off we were. Now, from the previous lesson, you will know that the steepness of the slope tells us how far off we are, right, from the minimum. Because at the minimum, the slope is equal to 0, and everywhere else it's equal to some number that isn't 0, right? So our gradient is going to be equal to df of the previous x, yeah? So we're going to call our derivative function. We're going to pass in the temp value, so at the point where we are in our function, And I'm going to store the slope, yeah, at this point in a variable called gradient. So one thing you might ask at this point is, why is calculating the gradient step 2, where we're calculating the error? What's the link between those two things? And the way to think about it is that the further away we are from our minimum, the steeper our slope. So if the slope is very, very steep, then it's indicative of being very, very far away from where we want to be. A steep slope means that we've got a high error. And if the slope is 0 or close to it, then our error is small. And now it's time for that adjustment step, for that learning step. So the new value of x is going to be equal to the previous value of x minus, because we've got to go down the hill, minus our step multiplier times the slope, times the gradient. And remember, this is the value of the slope at the previous value of x. So what we're doing here is we're taking a step that's proportional to the negative of the gradient of the function at the point that we're at. And then we're subtracting from the previous x value because we want to move against the gradient towards the minimum. And this is where the learning in machine learning takes place. So this loop is going to run 30 times. And after it's finished, let's print out our results. So I'm going to say the local minimum occurs at what? Well, the new value of x, right? Because that's what we're updating in our for loop. And we're going to print out the slope, yeah? So we just have to make sure our slope is close to 0, right? Or the value of dff of x, yeah, at, at this point. So this is going to be our derivative function, and as an input, it's going to get the latest value of x. Finally, we're going to print out what the cost is at this point. So this is the f of x value, or cost, at this point is, and this is going to be our cost function at the point where the cost is lowest. Now, before I run this, make sure you've got a plus sign here, because if you ever have to go to restart and run all, or run all above, yeah, then you may want to make sure that this loop doesn't continue going. I just caught myself out there. So I'm going to press Shift-Enter now here, and I get my print statements shooting off the results of our gradient descent. So what can we learn from this? What can we deduce from the values that we're seeing here? Well, the first thing is that we can see that they're approximations, right? This isn't an exact value. We're not getting a very clean answer here. But that might be the case because maybe we haven't run our loop often enough. So if I increase the value here from, say, 30 to 50, let's see what happens with our values that we get printed out. So one thing that we're seeing is that our slope is getting a lot closer to 0 here than before. The second thing is that this value here on f of x is also getting a lot more precise. And so is our new value of x. So it's getting much, much closer to a minus 0.5. Yeah. If I run this 500 times, let's see what happens. So as you can see, we're converging on this local minimum by brute force, right? We didn't solve our cost function here analytically. What we're doing is we're iterating and going down that valley, that cost function, until we reach the minimum point. And at the minimum, our slope is equal to 0, our cost is equal to 0.75, and this is when the x is equal to minus 0.5. So obviously, you can run this thing 1,000 times or what have you, right? But oftentimes, you actually know ahead of time how precise a calculation you need, right? From a resource management point of view, what you can actually do is you can tell the loop to stop running once a certain level of precision is met. And I'm sure you're looking up, you're scrolling up and you're looking at this while loop here and you're thinking, the while loop seems ideal for this, right? We can run the while loop as long as our calculation is within a certain level of precision. And you'd be right. That's exactly something you could implement if you wanted to with the structure of the while loop. Let me show you how to do this with the for loop as well. We're going to modify our code here a little bit to include a cutoff point for a certain level of precision. And the way I'm going to do this is by adding another variable up top. I'm going to say precision is going to be equal to 0.0001. Yeah, so this is how precise I want my answer to be. Now, where does this come into play? Well, what we're interested in with our precision estimate is what's the difference between the new x and the old x, right? So if those two are getting closer and closer and closer together, then our calculation is getting much more precise. So what we can do is we can say, well, the step size, is going to be the difference between our new x minus our previous x. Yeah, that's going to be the step size. And just to make sure that step size is always a positive number, we're going to say, well, what we care about is actually the absolute value of our step size. And change the number of times this loop runs to maybe 10. Yeah, and I'm going to print out the step size just so we can see how it evolves over time as the loop runs. So let me run this. Let me press Shift Enter here. And we can see here our step size initially starts out with 0.7 and then it decreases, right? The new x and the old x are getting closer and closer together. So we can see here our step size is decreasing. So I'm going to comment out this print statement so it doesn't execute anymore. And I'm going to add the condition for terminating this for loop. Yeah, I'm going to say, well, if the step size is smaller than the precision, so in other words, if the difference between the new x and the previous x is smaller than 0.0001, then we can terminate our loop. Then we can stop with our calculations. So put a colon there, and then the Python keyword for stopping this loop is called break. So I'm going to leave it at that. And I'm going to say, well, run 500 times. Yeah, for loop, run from 0 to 500. But if the step size is smaller than our predetermined precision, then stop running. Let's see how often our loop runs according to this logic. Well, we don't know, right? Could have run any number of times. We probably have to print the value of n. So print loop ran this many times. Whoop. Forgot the S. So given these constraints, our loop ran 40 times. Yeah, it's actually not that much, not that many times. If we add an extra 0 here on the precision that we're looking for and press Shift Enter again, we can see that it ran 50 times. So it actually never gets up to 500. Yeah, doesn't go up all that way. And that's because it reaches that terminating condition this break statement a lot sooner. But still, the way we wrote this code, we have two conditions where it can stop. It can either reach 500 and it will stop there, or when it reaches the minimum and that step size becomes very, very, very small, then it can also terminate. Now, running the Python loop and calculating the minimum is very well and good, but I'm a very, very visual person, and I'm sure you might be too, so I find graphing things very, very helpful. The way we're going to go about graphing it is, first off, we have to kind of keep track of all the values that we've calculated inside of our loop. So we're going to create two lists, two Python lists. One of them is going to hold on to our x values. So it's going to be a list, and it's going to contain the new x values. And the other thing is I'm going to also create a list for all the slopes. So I'm going to call this slope list, and it's going to contain whatever value our derivative has at this x position. Yeah. Now, within our loop, we're actually doing these calculations anyhow. So all we need to do is we need to append the x values and the slope values to our list. So I'm going to say xlist dot append to add a new value to it of the new x value. And this is the x value that we've updated after we've taken our step down the cost function. So we're going to append this value to our list, and also for our slope list, we're going to append the output from our derivative function at the new x value. Yeah, and that's it. That gives us the basis for plotting our charts. So let's do that now. I'm going to go up here, and I'm actually going to copy this cell here. I'm going to go to Edit, Copy Cell, and we're going to reuse it down here, a lot of this code. So I'm going to paste the cell above, and I'm going to edit my comment to say that we're going to superimpose the gradient descent calculations, yeah? So this is the goal. Now, we've got our two charts, and what we're going to do is we're going to add a scatter plot on top of these with the data that we've captured from our loop. Here's how we're going to do it. For our first chart, we're going to say plt.scatter, parentheses, and then we have to supply some arguments. So on the x-axis, it's going to be our list of x values. And for our y-axis, we want to feed our list of values into our cost function, right? So this is our f of x. Now, you might think I can actually just put the x list in here and press Shift-Enter. But this isn't going to work. We're going to get an error, yeah? And this is because our function, the way that we've written it, cannot process a list. It's unable to process this list as it is. So I'm going to have to do a little type conversion first. So I'm going to create a variable called values and set it equal to a NumPy array, which is going to take as an argument our list of x values. So our function can work with an array, but it can't work with a list. And if we press Shift-Enter, we should see that now we have a little scatter plot on top of our graph. But in terms of data visualization, that was very, very poor, right? So I'm going to say the color of these dots should be red. They should be a lot larger, so I'm going to set the size equal to maybe 100, and I'm going to give them a little bit of transparency. So I'm going to say the alpha should be equal to maybe 0.6. See how that looks. So this is looking a lot better. Yeah, so we can see here as our algorithm runs, going closer and closer to this minimum. But we can also show this on our second chart as well, right? So we can see how we're inching closer to where the slope is 0 on this right-hand chart. And we can do that by making use of the other list that we've captured. So in this case, it is a little bit simpler because we just have to write plt scatter parentheses xlist. X values still the same, but for the y values, we've done a bit of a calculation already. So we can say slope underscore list. Yeah. And let's also make it a red color. Make the dots big, size 100, and alpha maybe 0.5 or something. Let's see how it goes. Yep, it's looking not bad. But I do wonder if there maybe should be some transparency on the line itself. So if this thing had an alpha of, say, 0.6, would it look a bit better? Yeah. This looks better. Let's do the same thing with our plot at the top as well. Let's give this an alpha of 0.6 as well. Let's see. Or 0.7 perhaps. Or 0.8. Let's try. Yeah, this is looking pretty good. So we can see here that now we have our scatter plot superimposed on our derivative function, and it stops when the slope is equal to 0. And on the regular cost function, we're moving down and down and down and down into the minimum at the bottom of this parabola. You know, the cool thing is that we can even zoom in a little bit. Yeah, we can even do a little close-up of our slope. Let me show you what I mean. So if I take this bit of code here, copy it, and paste it, and say chart number 3, and call this the derivative close-up, and then I change the title and say gradient descent close-up. Might get rid of the Y label, don't need that. I'm going to keep the grid, but I'm going to change what's on the axes. I'm going to go from, say, 0.55 to minus 0.2. So zooming in here on the x-axis. And on the y-axis, I'm going to do the same. I'm going to zoom in from 0.3 to 0.8. I'm still going to leave it sky blue. Change the line width to 6. Alpha 0.8. Just change these values around a little bit to make it a bit more distinct. Yeah, make the dots a little bigger. And if I press Shift Enter now, then nothing will happen because I need to adjust my subplot, right? I'm adding a third plot here, so I have to make sure that I have, in this case, 3 columns, right? I've got 3 charts. This is chart number 3 of the lot, and this is going to be also edited to chart number 2, right? On the 3-column subplot. And same with this. This is chart number 1 on the 3-column subplot. And it's now that I can run this, see what happens. Aha. So I'd say this is pretty good, right? So we've got a close-up here where we can actually watch the gradient descent converge upon that 0 value. And you can see those steps getting smaller and smaller and smaller and smaller as we're getting closer to our goal. I think this is incredibly cool. The charts look a little bit squished. Maybe what I'll do is I'll change this from 15 to, I don't know, 20 on the width. See if that helps. Yep, that definitely looks a little better. Okay, brilliant. We've done quite a lot of work in this lesson. This has been a long and difficult lesson, but writing the code definitely helps us play around with the gradient descent. Yeah, because what we can do now is we can change a couple of these values and see how it behaves differently. So, for example, if instead of at 3, we start at -3 with our gradient descent, let's take a look here. If our starting value is -3, and I rerun the loop and rerun all the calculations and rerun the graphs, then we can see how the gradient descent comes in from the other side. So in this case, it's from the bottom here instead of from the top. So this is really, really cool in being able to actually play with the algorithm. And this is the advantage of writing all the code out and actually running it and rerunning it to see how differently it behaves. Because not only can we change the starting point, but we can also change, say, how many steps we're taking, right? So if we rerun our algorithm to only run about 10 times instead of the usual amount, then we can see how we're not getting that close to the minimum, right? So we should be getting about here, but we're actually not reaching it. So yeah, I think this is really, really cool. And in the next couple of lessons, we're going to be exploring a couple more of the idiosyncrasies and the strengths and weaknesses of this algorithm now that we've written it and graphed it. I'll see you there.